All right. Okay, we still have 5 minutes, but I just opened attendance. So if you want to go ahead and do attendance, you can. I don't. What you got?
I'm still not getting that left and right shift thing.
You're still not getting the what?
Don't understand the whole left and right shift thing.
Okay.
I don't understand. I want to memorize the table, but I don't want to because I feel like it's silly to memorize it.
Okay.
So where do you have any Zoom things open?
Zoom things open.
Like
Oh, yeah. So go to, watch, you go to Moodle. So you go
I'm
here.
gonna try to do, I guess not, it's not gonna be today, but maybe tomorrow.
Yeah. So see this link right here?
Uh-huh.
Just click that one and I'll show you all the open spots that I've got. And then just pick one that works for you.
Do you have something? Like, are you doing them tomorrow?
I do.
Okay.
I don't know if anybody's, so I have 10 o'clock tomorrow.
That's okay. I get off work at 2, so I was trying to do it around then, but that's okay. I'm gonna try to.
So when you look at those left and right shifts,
I do. The first part fine. It's the shift that I just can't.
you have
I
to
want to
think.
do the opposite of everything I'm doing.
Yeah. You have to think about the reaction's always trying to stay at that original equilibrium.
Mm-hmm.
Like that's the sweet spot.
So like if you start on the left side.
It depends on if you're going up or down.
Okay.
Right? You can't always say if you're on the left or you're on the right. You have to think about, are you increasing a reactant or decreasing a reactant? Because you'll have the opposite effect.
Okay. I tried to redo the homework and I still got it wrong.
Like completely opposite?
Yeah.
Okay. So think about like if you lose a reactant, right? If I take some away, well, the reaction is going to try and recover from that and shift back to what it was before.
Okay.
So how do you get back to that? If I take away a reactant,
you're gonna make more reactant.
Okay. How do you make reactant? Do you go in the forward direction or the reverse direction?
The reactant's on the left side, so I'd go on the left.
So you go towards the left. You would go in reverse. That's it. That's it. Maybe you don't need to draw the arrows up and down. Like,
I don't know.
try not to do it.
Okay.
Don't draw arrows.
And see what happens.
Just think about it. Some people it works for, and some people it doesn't. And if that part doesn't work for you, do it a different way.
Okay. I'm so scared there's gonna be a bunch of them when they test it. I'm gonna screw it all.
It's not gonna be. There's too many different things.
Oh, I know. I know.
So try without drawing the arrows.
Okay.
And see what you think.
Okay. I'll try, and then if not, I'll email you.
Yeah.
Maybe you can.
And maybe we can find a time outside of normal. Okay. All right. So I'll leave it up on attendance. Okay. All right, we're just about ready. So if you have not already, please go ahead and check in on attendance. Okay, so we'll go ahead and get started. So happy Thursday, everybody. This is our last regular class, right? Because we have an exam on Tuesday, okay? So your homework is due on Monday night for chapter, what are we on, chapter 10? No, chapter 9, So your homework for chapter 9 is due on Tuesday by 9 p.m., right? And then you have an exam on Tuesday. And it will be, the exam on Tuesday will be on Respondus, just like always. And if you want to come to class to take the exam, never a bad idea. Lots of people have had technical problems and been so happy they were here. So the door's open, I'll be here, okay? Let's see, what else? I made an announcement, there was one error in the ICP. I made an announcement on the error in the ICP on the announcement forum. Y'all are getting announcement forum emails, right? No, okay. You need to change your settings on Moodle so that you get an email whenever one of your professors posts something in the announcement forum. That's I think you can go into your, like when you're in Moodle where your picture is, I think that's where your settings are. So that's a good thing for the future. Okay, is today the last day to get iClicker points? No, we will have some more iClicker points on Thursday. We won't have them on exam day, but we will have them on Thursday, okay? All right, get ready for your joke of the day? All right, what did the left eye say to the right eye? Something smells between us. I thought it was good. All right, so you should have done your attendance. Let's pull up a few iClicker questions. All right, so we got 73 in today. All right. Okay. So the first one is to select the strong electrolyte. When I say strong electrolyte, what's a strong electrolyte? If y'all answer, I will help. This would be a strong base or a strong acid. How do I know something is a strong acid? It's what? I bring clay, IBrCl, so HiHbr, HCl, I bring clay, or then hydrogen's good. Awesome, 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 awesome. And my strong bases? Group 1 and part of group 2, but really group 2 is really only strontium and barium. Okay. All right. So now, can you select the strong electrolyte? Remember, 1.5 minutes. Well, 8 seconds. All right, so let's look at each of them and let's see what we picked. Let's see what y'all picked. Okay, so the majority did pick B. So let's look at A. What is A? It is a base. I'll agree with that. It is a base, but what kind of base? It's a weak base. Why? Mg is in group 2, but it's not strontium or barium, so it's not going to be a very strong electrolyte, right? It's not going to completely disassociate, right? Our strong bases or our strong acids are going to completely disassociate. So that's why we say it's KOH, because if we put KOH in water, what's going to happen to the KOH? It will completely disassociate into ions. MgOH2, not so much. MgOH2, but only some of the particles will disassociate, not all of it. That's why it's weak. NH3. It's a what? It's a weak base, right? What's the definition of a base? Will accept a hydrogen, right? An acid, whoa. An acid will what? Donate. A base will accept. Okay. All right, HNO2. This is an acid, but we have 1 hydrogen and we have 2 oxygens. So we only have 1 more oxygen than hydrogen. So this one's going to be weak. So the only one that was correct was B. Okay. All right, let's try another one. According to the Bronsted-Lowry theory, NH3 is a base because we just talked about this. Okay, 10 seconds. Okay. So, what did we say before? A base does what? And we said protons, H plus. Are protons and H plus the same thing? Yes, it accepts protons from water, right? So you have NH3 that becomes what? Okay. All right. Okay. So now we're going to talk about the opposite side. We talked about a base. Let's talk about an acid. So according to the Bronsted-Lowry theory, when an acid is dissolved in water, did I mark the other one correct? I don't think I did. I'll go back and do it. 10 seconds. Okay. So what does it do? Y'all told me already. It what? It must donate a proton. So we're between C and D, right? So we know it donates a proton. Does it form a conjugate base or does it form a conjugate acid? It forms a conjugate base, so it should be C. Good. Let's see, I think I can go back. Was it C on this one? Yeah. There we go. Okay. All right. So now you might want a sheet of paper. I don't know if you can look at it and do it, but you might want a sheet of paper just so that you can kind of work through it. All right, so select the correct equation for the neutralization reaction for H2SO4 and KOH. Remember, what are two things that you make in a neutralization reaction? Water and a salt. Water and a salt. I'll give y'all 2 minutes on this one. Okay, 10 seconds. I'll give y'all until 2 minutes, 5 seconds. Okay. All right, so when you were looking at this, you're looking for one that has H2SO4 and starts with KOH, right? So I all of a sudden know that this one's not right because it doesn't even have my correct reactant there, right? So when I look at the rest of them, what's kind of different about them? The coefficients are different, right? So water, sometimes we have a coefficient, sometimes we don't. And on one of our products, sometimes we have a coefficient, sometimes we don't, right? So we're going to have one hydrogen over here, right? One hydrogen from here going to react with one OH from here. But how many hydrogens do we actually have in our H2SO4? 2, right? So if I were going to write my balanced chemical equation, if I have H2SO4 plus KOH, what's going to end up happening is that I'll have 2 hydrogens from here. So how many OHs will I need to make 2 things of water? I'll need 2, right? And you could balance it after when you write it, it doesn't matter. And then what else am I going to make? I'm going to make my salt. So I'm going to start with my cation, which is potassium. Then I need my anion, which is SO4. But what did you notice about when this SO4 is in a bond with hydrogen? How many hydrogens do we need? 2. So what does that make the charge on SO4? So SO4 has a charge of 2 minus. So if I put that with potassium, what's the charge on potassium? Plus 1. So I'm going to have to crisscross my charges. So I'll get K2SO4, right? Am I balanced? No, what am I missing? I need 2 here because that will give me 2 potassiums and it will give me the 2 hydroxides I need to make the 2 waters, right? So you should have picked, what are we doing? E. You should have picked E. So what did y'all pick? E. All right. Good. Okay, let's do one more. Now this one you don't have to balance. This one is just asking you what are the products, okay? So if you have a reaction of HCl and NaHCO3, remember what we talked about? You made something different when you had a carbon. So what do you get when you react HCl and NaHCO3? A minute and a half. Ten seconds. Okay, so you know that we're going to neutralize, right? So we're going to make water and salt, but what else do we have here? We have a carbon, right? So we have, if we have HCl, I don't know what that other L was. HCl plus NaHCO3. What's going to happen is we're going to make water, right? We're going to get a hydrogen from here. We're going to get some oxygen over here, right? We're going to make a salt, sodium, and we have chlorine, so that's NaCl, that's our salt. But what are we left with? We have carbon and oxygen left over. So carbon and oxygen together is going to make a gas. What gas is it going to make? Carbon dioxide, CO2. So water, CO2, and NaCl. You didn't have to balance this one. Good. Good. Okay. So let's go back to our in-class problems. And I think we were on like 9.3. Did we get that far? We finished 9.28, so 9.30. Okay. Thank you. All right. So this is kind of wrapping up our equilibrium stuff, right? This is really the practical application of equilibrium. We know that when we exercise, we're producing energy, right? You have a meal, you have a source of energy there, and we need to metabolize that glucose or whatever it is that was in your meal in order to produce energy. But something else happens as well. What else do you need in order to survive? Oxygen, right? So if we look at a chemical equation for the production of energy, what we're going to take is C6H12O6. What is that? Glucose, sugar, right? We're going to take glucose. We're going to add oxygen to it. Remember, this is a combustion reaction, right? And so we're going to make carbon dioxide, water, and energy, right? So if we exercise, why are we going to breathe faster when we exercise? What does exercise do? Well, what? When you exercise, right? Your body's saying, I need energy. How do we get energy? We have sugar and we have oxygen. We slam them together in combustion, basically, and we get energy out. So the more you exercise, the more you need to eat, right? The more you exercise, the more you need to breathe. So when we exercise, we're depleting glucose, right? What else are we depleting? Oxygen. We're depleting oxygen. So when we exercise, exercise will reduce the amount of reactants, right? And so in this case, we're talking about O2. If by exercising you reduce the amount of O2, why do we want to breathe faster? Because we're trying to get back to equilibrium, right? We want our reaction to go. Well, how can we make it go? We can breathe faster. So your body has basically sensors inside of the brain that monitor the amount of carbon dioxide levels in your bloodstream. And if those carbon dioxide levels get too high, guess what you start doing? Right? You start breathing faster. What happens after you finish running and you rest? What happens to your breathing rate? It slows back down because your carbon dioxide levels go down, right? And therefore your body's like, oh, I don't have to breathe as fast, right? So exercise will reduce the amount of reactants. So we breathe more to replace the O2 or the reactant, right? This one, it's technically reversible. It's technically reversible. You can use up energy and make sugar, like in plants, right? You can use sunlight and you can make sugars. So whether or not a reaction is energetically able to go in the forward and the reverse reaction is one thing, and whether it's going to happen in real life is something else, right? Because we could say what happens in the body, what happens out in the world, right? If you have combustion going on in your car engine, are you going to make that go in reverse? There's no way, right? Because all those gases escape out into the air. But if you were able to hold them all together, yes, you could make it go in reverse. But under normal physiological conditions, that'd be a no, right? So it depends on the condition. Okay. All right, so now we're talking about weak acids and bases. So you'll get these tables, you'll absolutely get these tables. But you have to be able to understand what the values inside of the tables mean. Here they're listing common strong acids, but you already know them, so you've got that covered. But what we need to talk about are Ka values. Ka values are dissociation, right? What's a K? It's an equilibrium. We would do our products over reactants, right? So a K value is going to tell us how easily the hydrogens are going to pop off of the acids, right? The easier it is to pop off, the stronger the acid is. And so therefore you're going to have a Ka value that's relatively big, right? You come down here, look at this Ka value of water. What's the Ka value of water? 1 times 10 to the negative 14. Do you know how small that number is? Right? 0.00000. How many zeros do I need to write? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, and a 1. Right? Is that a big number or a small number? That is a really small number, okay? So if you have something with a really small Ka, the hydrogens aren't going to come off very easily. They will, but not very easily. So is it okay to put your hand inside of water? Yeah. Is that a strong acid? No, right? But do you necessarily want to do that with phosphoric acid? Yeah, probably not so much, right? Okay. So all you have to do is use the tables and identify which acid is stronger. So I'll give you this whole table. What I will not give you is this little arrow right here. Y'all understand what I'm saying? I'm not going to give you this arrow on the exam, but I'll give you the table. I will absolutely give you the table. Absolutely.
Yeah, that's what I just said.
Am I going to rearrange the table? No, I'm copying and pasting it from the book. No. All right, HCN or H2CO3. I'm going to have to keep like scrolling back up. So HCN or H2CO3. Which one is stronger? H2CO3 or carbonic acid. So all you have to do is look at their Ka values. This one's 4.5 times 10 to the negative 7. This is 6.2 times 10 to the negative 10. The closer you are to water, the weaker you are. If you just remember that, the closer you are to water, the weaker of an acid you are. Okay? H3PO4 and H2PO4 minus. So we've got H2, no, I'm sorry, that's H. Oh, I'm looking at the wrong one. H2PO4, because I can't see everything at once. H2PO4 minus, here we go, this one, dihydrogen phosphate, and H3PO4, phosphoric acid. Which one's closer to water? Is dihydrogen phosphate, so this one's weaker. So the question is, which one's stronger? H3PO4 or phosphoric acid. Okay. HCl or HSO4? Well, here's HSO4. It's at the top of my list. Where's HCl? My HCl's over here. Remember when we made our list of strong acids and bases, right? We said the strong acids are I bring clay. Well, there's your clay, right? Now I know that this one also has, this is 1 hydrogen, this is 4 hydrogens. So we do have 2 more oxygens than hydrogens, we do. But this one's kind of on the edge. And so sometimes it's labeled one way, sometimes it's labeled the other way. But we know HCl is an extremely strong acid, right? So you'll have both tables. All right, now we're going to look at some equations and we're going to see what happens when we put these substances in water. So when you look at these are all acid-base reactions. So we're going to identify an acid, we're going to identify a base, and then what does the acid turn into? A conjugate base. What does the base turn into? A conjugate acid. Okay, so I kind of like to start with water. This is really similar to what we did before. So what's water acting like in this case? It's accepting, so it is going to act as a base. And then what does it turn into? Conjugate acid. Why do we say that H3O plus is a conjugate acid? What could it do? It could go in reverse, right? And if it went in reverse in this reaction, what would it form? But it would form a base. This is the base, and here's the hydrogen I'm donating, right? Because an acid donates a hydrogen. Okay, so always remember that you have a double-sided arrow, and that's why you can kind of do this. Okay, so how about H3PO4 and H2PO4 minus? The H3PO4 is the acid, and the H2PO4 minus is the conjugate base. The conjugate is basically what's left over. And if you go in reverse, then you know if it's an acid or a base. All right? So let's do the next one. I always like to start with water. It just makes it easy for me. Okay, what happened to water in this case? What did we do? We're donating something now. We're donating a proton. If we donate a proton, what are we? We're an acid. So we had an acid, and we're going to turn into a conjugate base. So what does that make CO3 2 minus? That makes this one the base, because it's going to accept the hydrogen, and that makes the HCO3 the conjugate acid. What do you mean you won't have the same thing on one side? Nope. Nope. That's a good question, but no, you won't have 2 acids or 2 bases on the reactants. Okay. All right, H3PO4 and NH3. Let's do the NH3. That one's kind of an easy one to see. So what's happening to my NH3? It is going to accept a hydrogen. So accepting a hydrogen makes you a base. And now that you've accepted it, now you have an extra hydrogen, so you are a conjugate acid. H3PO4 going to H2PO4 minus. H3PO4 is giving up a hydrogen, so that makes it an acid, and it turns into the conjugate base. What's the difference between an acid and its conjugate base? One hydrogen, which does have an effect on the charge. But really the difference is a hydrogen, okay? All right, so now write the formula and name of the conjugate base formed from each of the following acids. So if we have an acid and we're going to form a conjugate base, If we have an acid, just like this, and we form a conjugate base, what happens to my number of hydrogens in the molecule? We're going to decrease, right? Okay, because an acid donates a hydrogen. Okay, so how would I write A as donating a hydrogen? CO3, what's my charge? If I give up a hydrogen, I'm going to be 2 minus, right? Because I'm giving up something that's positively charged. Yeah? So whenever we're forming a conjugate base, we're give up hydrogen ion. So remember that hydrogen ion is positive. Rachel, more practice problems are at the end of the chapter. They're called additional problems. Very good. Y'all got me. All right. H3O plus. Give up a hydrogen. So that'll be H2O. What's my charge? Neutral, because I'm losing the positive. Okay. HPO4, 2 minus. Give up a hydrogen, so I'm just not going to write it. And then PO4, now my charge has to change. What does it become? I'm giving up a hydrogen. 3 minus. 3 minus. Right? I know it's like one of those you got to kind of think in reverse sort of deals. All right, HNO3, I'm going to get rid of my H. So I'm going to make NO2. NO2. All you're doing is getting rid of the H. I scratched it out, but it's still there. Maybe. See? So every time that you lose a positively charged something, you're becoming basically more negative, right? You do not need to name these. You could. Where could you find these? Polyatomic ion chart. These are all polyatomic ion chart, and then you know water. Oh, it is named. You do have to name. Okay. Where could you find the name? CO3, 2 minus. Yeah, what is it? Carbon what? Carbonate? H2O. You could say water, or what was the real scientific name for water? Y'all remember? Dihydrogen monoxide. Okay, PO4, 3 minus. Phos what? Phosphate. And then NO2 minus. Nitrate, nitrite, what are we? Go look on your polyatomic ion table. Nitrite. Okay. Let's see. All right, so now we're going to go in reverse, right? We're going to write the name and the formula for the conjugate acid formed from the following bases. Okay, so we have a base and we're turning into an acid. How are we going to turn into an acid? Sorry, y'all. So if I have a base and I'm going to a conjugate acid, a base will do what? Accept a hydrogen. Okay, so we're going to accept a hydrogen. SO4, 2 minus. What are we going to make? H. SO4 minus 1, because we have what? Because we're adding a hydrogen so that we are making something that is now going to be more positive, right? Last time we were making something more negative, now we're making something more positive. Okay, we're going to name it. So go to your polyatomic ion table. What is SO4 2 minus? Sulfate. Okay, what do you have to remember? Well, so if it's charged, it's going to be an ion still. So you don't necessarily have to make an acid out of it. If it's uncharged, you can call it an acid. If it's charged, it's polyatomic. It's got multiple atoms in it and it has a charge in it. So go find that on the polyatomic ion table. What is HSO4 minus? Do you find that? It's page hydrogen sulfate. Okay, so all they did was they took the root, which was sulfate, and they said we added a hydrogen to it, so we're going to call it hydrogen sulfate. Okay, so how about Cn minus? Add a hydrogen to it. What do you get? HCN. So you could call this one hydrogen cyanide because what is Cn? Cyanide. I don't know if I spelled that right, but it's cyanide. So you could call this one hydrogen cyanide. That's fine. I think your polyatomic ion table names it as an acid because it doesn't have a charge. So you could go either way with this one. So if it were an acid, how would I name it? This one's kind of weird. We name this one as if it were a binary acid. So we would name it hydrocyanic acid. Or you could name it hydrogen cyanide. Either one's correct. Either one's fine. Okay. OH minus what? The first one's what?
The first thing that you did?
Sulfate?
No, B, the first one. Hydrocyanic acid isn't on you.
I know, I'm telling you, you could do it either way. Because it's neutral, you can name it as an acid. You could also pull it from the polyatomic, but it's not really a polyatomic. It's not really charged. So you could go either way, doesn't matter. Either way is fine. OH minus. Just be water. You could write it HOH. Okay. ClO2 minus. This is the chlorite ion. What do we turn into? No charge. So what could we name it? We could name it as an acid, or we could name it hydro. And what is ClO2 minus? Chlorite. Chlorite. Okay, so you could name it hydrogen, HYDROG, hydrogen chlorite, or how else could we name it? So remember, if you have a polyatomic, you went to a chemistry class and you got 8 IC, ITE, OUS. So I got ATIC-itis, right? So if I did ITE, I'm going to end it in OUS. So this is chlorous acid. What? There's some that y'all are familiar with, and the ones that you're familiar with don't sound weird. But it's just because you haven't heard them before. That's all it is. Chlorous acid. Okay. That's the only thing. All right. Complete the following reactions and identify the conjugate acid-base pairs if the named reactant acts as a base. Okay, so what we have to say is whichever one in here is named, That is going to be our base. So this one, we're giving you pyruvate and water. So pyruvate's a product of glucose metabolism when you go through glycolysis. And so this one, pyruvate right here, is going to be a base. So what's going to happen if this is a base? We're going to accept a hydrogen, right? So we're going to go CH3, CO, CCO, O, what? H. I think I put one too many carbons in there. There you go. So now we don't have a charge. What else do we make? What does our base do? Okay, so where did the H plus come from? It came from the water. So what else is left over from the water? Just OH minus. So this is aqueous. This is aqueous. So we identified our base, and we have to identify the conjugate acid base pairs. So if we have a base, what did we make over here? Conjugate acid. Okay, so then what else do we have over here? Here's our acid, and here's our conjugate base, right? Don't forget that. All right, B, dihydrogen phosphate, a component in cell buffering. Remember, it's going to act as a base. So what's that base going to do? It's going to pick up a hydrogen. So instead of having 2 hydrogens, how many hydrogens am I going to have? 3. What's my charge going to be? Neutral, because I was negative. I picked up a positively charged hydrogen, so now I'm neutral. Now, where did the water come from? Where did the water come from? Where did the hydrogen come from? Water. So what's left? OH minus. They're both aqueous. So now we need to identify. We said this was a base. That makes whatever we made from it the conjugate acid. That makes our water the acid, and then our OH minus the conjugate base. Okay. All right, bicarbonate, a component in blood buffering. So we're told this is a base. So what does that have to make the water? Must be an acid, right? Okay, so our base is going to accept a hydrogen. So we had 1 hydrogen, now we're going to have 2, H2CO3. What's my charge? Neutral, it's aqueous, and we gave up our hydrogen, so we have OH minus. Okay, so our base turned into a conjugate acid, and our acid turns into a conjugate base. Okay. All right. Now, this is a little bit that you, I'm sure, probably already know. This little bit right here, when we talk about a solution being acidic or basic, it's the pH scale. Have you ever seen those little strips of paper, right, that change color when you put them inside of an acidic solution or a basic solution, and then you just match the color to the pH? It's just an indicator. It's a dye inside of the paper, which will change color depending on the pH. So if it's basic, we're going to be above 7, right? From anywhere from 7.0001 to 14, right? If you're neutral, there's only one way to be neutral. If you are pH 7. Acidic is below, right? So like hydrochloric acid, that's like a pH of like 1 or 2, right? It's really, really low. Okay. Bad bases are really, really high. Bad acids, strong acids are really, really low. Things that are close to neutral are weak. Okay. So we can relate the acidity to the concentration of hydronium ions, or what's another way to write hydronium ions? Just plain old H+, right? But they don't really exist in solution that way, so we don't always draw them that way. We can look at their concentration. That's what actually gives us pH. If something is dangerous to you, it's dangerous because it has too many hydrogen ions. If it's a base, it has too much OH, right? And so you can always look back and see what's the concentration. In order to do that, in order to switch between pH and concentration of hydronium ions, you have to do what's called the negative log. That's what P means. When chemists were using the pH scale, they kept using all these crazy exponents and nobody understood what it meant. Like you couldn't look at the number and say, oh, that looks neutral to me. Oh, that looks acidic to me, right? But if I give you a pH, if I say pH 8, what am I? Acidic, neutral, or basic? Basic, right? You got that right away. So this is a way for us to very easily communicate in science. That's why we do it this way. But a lot of times we need to know the actual concentration of hydronium ions so that we can do an experiment or make something work. So it's important to be able to switch between the two. So to go from pH to concentration of hydronium ions, right? All it is the negative log. So let's try and look at some of these. Oh, and before we go on, and I lose this, when you want to go in reverse, right? When you want to go back and forth, if you're trying to solve for the concentration of H3O plus and you're given the pH, you do in your calculator 10 raised to the negative pH, right? So we'll practice this on the calculator, and on the videos, I was able to video my calculator, which I hope helped y'all to be able to do that. All right, so let's do some. If we have soda, which is pH 3.2, acidic, neutral, or basic? This one's acidic, right? Shampoo, 5.7, acidic. ACID, yeah, I see. Okay, laundry detergent, pH 9.4. This is basic. Rain, pH 5.6. Acidic. Now, a lot of people think that the stuff that we use is all neutral in our lives, but it's not true. Like Charles got pH paper one year for Christmas. This is how strange it is in my family. He got pH paper for Christmas. He loved it, FYI. He had to go around testing everything in our house. Every liquid in our house had to be tested. Every chemical, everything in the fridge. It was absolutely hilarious. But he soon discovered not very much was neutral. But that's one thing that you would definitely see. Okay, state if each of the following solutions is acidic, basic, or neutral. You could take these and you could convert them to pH, which is what we're going to actually do in a minute. But you can also look at them and actually kind of guess. You won't get a perfect answer, but you can kind of guess and you can know if it is acidic or basic or neutral, right? Because if you come up here, right, if you have something that's a pH of 7, what's your exponent going to be? 10 to the negative 7. So if you have an exponent, and you also have to have it being 1 times 10 to the negative 7, but if you have an exponent of 10 to the negative 7, you're really close to neutral. If you have something that is like 1 times 10 to the, let's do basic. So if I want something that's less than 7, what's my exponent going to be? If I want to get something that is smaller than 1 times 10 to the negative 7, I want to go smaller. If this is 0.1, 2, 3, 4, 5, 6, 7. I want something smaller. 0.1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. So now I'm 10 to the negative 8. And that should have been a 1. I don't know why I put a 7. It should have been a 1. 1 times 10 to the, right? So what's going to happen to my exponent? It's going to become more negative, right? If I have something acidic, it's going to be greater than 1 times 10 to the negative 7. So maybe this is like 0.003, right? Because that would only be a negative 1, 2, 10 to the negative 2. So you can just look at the exponent and kind of know. Okay, do we have anything that's at pH 7? No, there's nothing that's going to be neutral, okay? So 10 to the negative 10 is going to be what? Basic. Okay, 10 to the negative 8. We're above 10. We are less than 10 to the negative 7. So we are basic. 10 to the negative 2. Whoa, that's acidic. Acidic. 10 to the negative 6. Well, we're getting close to neutral, but we're acidic. Okay, so you can just look at them and know. All right, so now we're going to take those exact same problems and we are going to solve for the concentration of H3O plus. I did not bring a calculator today, but if you need to be able to do this on the calculator that you're going to use on the exam on Tuesday. So it is super, super, super important that you are able to do this. So if you have your calculator out, you know I love those clicking sounds. Right. Okay. So I need to calculate the pH. What's my formula for pH? Negative log concentration H3O plus. So my pH is equal to the negative log of this number right here, 5.6 times 10 to the negative 10. So what do you get? Uh, 9.25. That's what I got. So is it easier to know if this is basic or acidic with this number? Right? We know that this is basic. It's much easier to look at pH than it is to look at concentration of H3O plus. All right, so let's do B. pH is equal to negative log 6.2 times 10 to the minus 8. What do y'all get? 7.21. Try typing it in again. And use that little negative sign at the bottom of the calculator and not the minus sign, because some people go wrong there. Oh, okay. All right. So then C, pH is equal to negative log 5 times 10 to the minus 2. So what is C? Now, whoa, that's very acidic, right? Wow. This one was basic, not very much, but still it's basic. And then the last one. What do you get? 5.74. Oh my gosh, I did it twice. Thank you. All right. Now we're going in reverse. Got a tickle in my throat. Now we got to go, this is like the challenging way on the calculator, right? We're going to have to do the opposite. So we know that pH is equal to the negative log, sorry, H3O plus, right? I want to solve for this. So what am I going to do? Well, I'm going to move the negative sign first. pH is equal to log concentration H3O plus. Now, I can't like divide. I have to take the anti-log. What's the opposite of a log? It's 10 to the, you know, like the little caret, but you don't have to put the caret if you're writing it that way. Come on. To the negative pH. So what I'm basically doing is saying 10 to the negative pH, 10 to the log cancels each other out. If you've never worked with logs before, that probably means nothing to you. But if you look on your calculator, you will see log and 10 to the on the same button. They're opposites of one another, right? It's the opposite function. So all you have to do is press second log to get that 10 to the function, okay? Equal to concentration H3O plus. So put in your calculator for A, 10 to the negative 12.10, and you will get the concentration. So I guess I need to erase this so I have room. So round two, what do they give you in 2 sig figs? So what do you get? 7.9 times 10 to the minus 13 molar. Now, you got to put the units on there. You have to know that that's molar. Okay, coffee, one of my favorite drinks. 10 raised to the negative 5.5. What do you get? 3.3? 3.2 times 10 to the negative 6 molar. And depending on how many digits you have here will translate into different numbers of significant figures, but I am not teaching you significant figures with pH. So when you do the calculation for the exam, just pick the choice that gives you the closest one to one of the answer choices. Okay, I'm not testing you on significant figures on pH. Okay, gastric juice. Ooh, this is your stomach juice. That's what gastric means. So 10 to the negative 2 is 0.01. We'll do it to 2 sig figs, 10 molar. Or you could just say 1 times 10 to the negative 2. Well, if you want two significant figures, that's 1.0, right? Okay, toothpaste, 10 to the negative 8.3. And to the negative what? 9 molar. Okay, so if you're not getting that on your calculator, please get some help. Please stay after and let me help you. Will the, say it again? No, it actually will be. Because it's over, right? We said it was like 1 times 10 to the 7 is pH 7, but it's no longer 1. If it's more than 1, it'll push that pH. Yeah. Okay. All right, pKa's. So remember how we said a P was the negative log? So if you're doing the negative log of pH, that's the, if you're doing, I'm sorry, the negative log of the H concentration, that's pH. Well, just like we said we have a K, we can do the negative log of the K so that we get a number that's understandable, right? All these exponents are really, really hard to understand, but if we convert them to negative logs, They're much easier to understand. So if we look at these pKa values, these pKa values will tell us the strength of the acid. So what did we say was our very, very, very weakest? Water, right? So if you kind of remember that, do you need this arrow? No, right? Always remember that water is going to be very, very weak. It disassociates that hydrogen ion, but not very well, right? And so as we lower our pKa value, we are increasing our strength. So it's an inverse relationship. But if you just remember that water is the weakest, W and W, you're going to be okay. And then you can figure out the rest. Okay? All right. Determine the stronger acid from the following pairs of weak acids. And this really is not a weak acid, right? I don't really like this question, but it's okay. HCl or HCN? Do we even see HCl on here? No, I see HCN, but I don't see HCl. Well, why is that? Because this one is what? This one is strong. It's a very strong. So determine the stronger one. Well, I just have to know that this is weak and this is strong. So there's my stronger one. Okay. Acetic acid or ammonium ion? So come up here for acetic. And what do we say? Acetic acid or ammonium ion? Here's our ammonium ion. So which one is stronger? The acetic acid. Okay. Carbonic acid or bicarbonate? So here's bicarbonate and carbonic. Which one's stronger? Carbonic acid is stronger. I always want to circle the other one. Ammonium ion or hydrogen phosphate ion? So we are ammonium and hydrogen what? Which one? Hydrogen phosphate. So hydrogen phosphate and what is ammonium again? I keep going back and forth. Ammonium. So between these two, which one's stronger? Ammonium. Not too bad, right? Okay. All right, now, if I give you pKa values, you can figure it out too, right? You don't have to figure it out from a table. Which one's a stronger acid? Niacin, pKa of 4.85, or acetyl salicylic acid? Y'all know what acetyl salicylic acid is in? Aspirin. It's an aspirin. That was like my first chem lab was making aspirin. Remember that? pKa of 3.5. So which one's going to be stronger? So remember, water is very, very weak. So whichever one has the smallest pKa is going to be the strongest. So our smaller pKa is acetyl salicylic acid. Okay. All right. So pKa is really important when we're making drugs because a lot of times, whether or not you can get the drug into somebody's system will depend on its chemical nature, right? We know that certain things cross the membrane and other things don't, right? So what do you want? What kind of state do you want your molecule to be in to cross a barrier, like a membrane? Do you want it to be charged? No, we don't. We want it to be relatively small and we want it to be uncharged, right? We want it to be neutral. That's the way it's going to get through the membrane the easiest. So when we design drugs, we're going to design drugs so that if it's an ingestible drug, right? What's going to happen to it when it hits your stomach, right? Your stomach's what kind of pH? Very acidic, right? So it'll be one thing when it's in your stomach, but what happens when it goes into your intestines? The pH is going to change. And so that's going to change whether the molecule is charged or not. And hopefully, once it gets to your intestines, then it becomes neutral and it can go into your bloodstream, right? And so that's how a lot of medications work, is that in certain parts of the body, they have a certain pH. And and then they can get across the membrane or do whatever it is, right? Okay, so let's look. Here we go. Here's an anticonvulsant medication. They're telling us this is the structure. They're saying that this is an acid, right? What does that mean if it's an acid? It can give up a hydrogen, right? Look at that hydrogen right there, ready and primed, ready to give up. The pKa of the acid is 4.8. So that's telling us basically this is the pH where we're going to change the attachment of this hydrogen to this molecule, right? So which form is charged? The acid, the conjugate base, or both? Well, what is it right now? It's an acid, and what's its charge? It's neutral, right? If we convert it to the conjugate base, what's going to happen? This arrow means that we are going to donate a hydrogen ion, right? Yeah? So then my structure becomes something, and I'm going to attempt to, I'm going to attempt to redraw this real quick. What is my structure now? My structure is now negative. It's charged, right? So which form is charged? Acid, conjugate base, or both? Conjugate base. All we did was put it in a structure instead of writing a formula, right? You already did this. You know this. Which form will predominate in the first part of the small intestine, the jejunum, where the pH is between 6 and 7? So we're saying that the pKa of this is 4.8. So when we get to the jejunum, we're almost neutral. Are we at this pKa? No, not anymore, right? So what's going to happen to this as soon as we get to something that's neutral? This is our pH 4.8. So when are we going to donate that hydrogen? What's going to happen? We'll become the conjugate base when our pH does what? Goes up or down? Goes up. Good. So what are we going to make in the jejunum? Conjugate base. I know. You kind of get lost in it. Okay, so which form, acid or conjugate base, will be able to easily diffuse through a cell membrane? The uncharged form, the acid uncharged form. So this is going to actually be absorbed in the body earlier than some other medications, right? Where we still have a pretty low pH inside of the stomach. Okay. All right, now this gets a little bit complicated. This really does get a little bit complicated. All right, we have a neurotransmitter. Y'all know what a neurotransmitter is? It's the chemical inside of the brain, right, that controls firing of neurons. So dopamine is one of them. It has a pKa value of 8.9. All right, so here's our drug, and it's in the acid form, and it's positive. Okay. Will the acid or the conjugate base predominate at the following pH values? So we got 3 pH values that we're going to kind of look at. So I'm going to put them over here: 7.45, 8.90, and 13.40. So we want to know 3 different things, right? A, which one's going to predominate? Then B, is it charged or uncharged? And then C, calculate the ratio of conjugate base to acid. So how are we going to do this? Well, let's talk first about what's going to predominate at the pH. So if we're at pH 8.90, what's going to predominate? Well, so here's the thing. This pKa is the actual pH at which this hydrogen is going to pop on and off. So if you're at the pKa value, hydrogens are popping off and coming back on, popping off and coming back on. So basically what you have at pH 8.9, what's going to predominate? You're going to have half and half. You'll have half that have the hydrogen and half that don't have the hydrogen, right? Because that's the pH at which the change occurs. Okay. Now, what happens if we drop the pH? What happens if we go to 7.45? The acid form is going to predominate. So the acid form is the one that has the hydrogen attached to it. And that makes sense because there are lots of hydrogen ions floating around in acidic solution, right? So it has the hydrogen. How about when we bump it up and go up to 13.4? Now we're going to have the conjugate base, okay? So now at each pH, is that form charged or uncharged? Well, this is again half and half, right? So the acid form, is the acid form charged or uncharged? Charged. Conjugate base form. If we take this and we're an acid and we lose a hydrogen, what happens to our charge? It becomes neutral or uncharged. Okay. Last but not least, we have to calculate the ratio. We're going to calculate that ratio. It's the conjugate base divided by the acid, right? So let's talk about this 8.9 column first. If you're at 8.9 and you got half and half, that means for every 1 molecule of acid, how many molecules of base do you have? 1. So a lot of times we represent these ratios as fractions, right? So this is my conjugate base. This is my acid. Okay, so what should my value be for 8.9? What's my ratio? It's a 1-to-1 or just 1, right? However you want to say that. But a lot of times we represent it as a fraction. Okay. Tell me in the 7.45, what's going to predominate? We have way, way, way more acid than we do base, right? So is this going to be a big number or a small number? Remember, it's conjugate base on top, and we're going to have lots more acid. So this is going to be small. I know we're getting close on time. I just want you to understand the concept. All right, so what happens at 13.4? It'll be big because I'll have lots of conjugate base and not so much acid. So I'll have a very big number. Small number, big number. You can, but it's fine. Could have cut your losses at some point. Right, all right. Okay, so that is almost the end. That was the bicarbonate system, but it's okay. We did one. It's okay. It's okay. All right. Any questions? When's your homework due? Monday night, 9 p.m. When's your exam? Tuesday at noon. All right. Y'all have a great rest of your day. Have a good weekend. Study hard. I will send out, what's that? Chapter 10 is not on the exam. And it's not on the final either. Remember, cut your losses. Do your best. Keep rolling and cut your losses. That's what happens when we have 5 hurricanes in one semester. We don't have any more. Yeah, right. Exactly. Exactly. Okay. Anybody on Zoom need anything? All right. I'll let y'all go. Maybe. Okay. Let me end this. No. Why am I'm clicking all the wrong things.